We're going to use MATLAB to define transfer function model as well as state space model. We'll then use MATLAB to convert from transfer function to state space and vice versa. We are then going to visualize the open loop response of a plant to different inputs. We'll then draw the frequency response diagrams in MATLAB. Then we are going to conduct stability analysis of a plant using transfer function and using state space model. We'll then develop the closed loop transfer function of a plant that uses PI controller and then visualize its response in MATLAB. We are then going to discuss controllability as well as pole placement controller design in MATLAB. Finally, we are going to see how we can use Control System Designer and see how the tool combines all that we have discussed earlier on. So let us get started. So here we are in MATLAB. All that we are discussing have been divided into sections, and we are going to use run section for our discussion. So for defining transfer function, which is our first discussion, we just have to define the numerator polynomial as well as the denominator polynomial coefficients. So as you can see, this is our transfer function. The coefficient is just 1 for the numerator, and for the denominator we have 1, 3, and 10. So we just use the function tf, and the argument it takes are the numerator polynomial and the denominator polynomial. So running the section, you can see from our command window, this is our g, and this is our transfer function, which is in continuous time. So the next section is the state space model definition. So this is the general definition of state space model. As you can see, I just have to name my A matrix, which you'll do using this line, then name your B matrix, C matrix, and D matrix. So in order to define your state space model, you just use the state space function, and the argument it takes are A, B, C, D matrices. So running this section, as you can see, I have my state space model, which is named sys_ss, and I have my A matrix, B matrix, C matrix, and D matrix. So the next thing is the conversion from transfer function model to state space model. And in order to do that, I just have to use the ss command and then give it as argument my defined transfer function model. So if I do that and run the section, you can see it converts the transfer function model G into state space model, and I name it sys_ss2, as you can see. And here is the conversion: A matrix, B matrix, C matrix, and D matrix. So the next thing is the conversion from state space model to transfer function model. The same thing, I use the tf function and I give it my defined state space model. So doing that, it will convert it from state space model to transfer function model. So let me click on run section. So as you can see, it has converted my state space model into transfer function model. So the next thing is visualizing the open loop response of my plant to different inputs. So I created a new figure using line 20, and then I will use the subplot function in order to visualize the open loop response of my plant to different inputs. So the first plot is given using this line 21, and I want to visualize the step response of the plant. So I use the step function and then I give it as argument g. So the next response I want to visualize is the ramp input. So for the ramp input, I have to use the LSIM function. So it needs the time of my simulation and it needs the input as well as the plant. So for the time, I want to do my visualization between time 0 up to time 10 for a time step of 0.01. And for ramp input, you know that U is just equal to KT, where K is the amplitude of the ramp. So for this response, I want an amplitude of 1, so U is just equal to T. And then I use my LSIM function. I give it the plant, the inputs, and the simulation time. So the next visualization I want to do is for the impulse response. So for the impulse response, I just use the impulse function and I give it G as its argument. So finally, I want to visualize the response of my plant to sinusoidal input. I also use the LSIM command or function. So as you can see, I also define my time, and then I define my sine function, which is the input. I give it a frequency of 2, and this is the time. And then the LSIM will have as argument my plant, my input, as well as the simulation time. So I just have to run this section. So this is the figure, making it bigger. As you can see, I have my step response here. I have my ramp response here. So this line is for the output and this one is for the input. Then I have my impulse response of the plant, and here is the sinusoidal response of the plant. So the bigger one, the one with bigger amplitude is the output, and the one with smaller amplitude is the input. So the next thing we are going to discuss is the drawing of the frequency response diagrams, which we can use for frequency analysis. So I have created a new figure using line 39, and I will use my subplot in order to have all the diagrams in one diagram. So you can see for Bode plot, I just use the Bode function and give it as argument the plant G. For Nyquist plot, I use the Nyquist function and the argument will just be G also. And for the Nyquist chart, I use the Nyquist function and the argument is also G. So running this section, so this is the figure, making it bigger. So this is my Bode diagram, which draws my magnitude against frequency as well as phase against frequency. This is my Nyquist diagram, which draws the imaginary axis against the real axis of my S domain. And this is my Nyquist chart, which plots the open loop gain against my open loop phase. So all these diagrams, you can use them for frequency response analysis. So the next thing is stability analysis with transfer function. So for that, I can use my root locus diagram or use the fall function. So clicking on this section, so this is my root locus diagram, which I can use for my stability analysis. So I just have to observe the starting point of my faults. So as you can see, these are my faults and they are on the left hand side of the S-plane. Therefore, my system is stable. Otherwise, from this line, I have computed my open loop pulse for the transfer function. As you can see, they are all negative, which indicates that they are on the negative side of the S-plane and the system is stable. So the next thing we are going to discuss is creating our feedback transfer function, which is given by this diagram. So the closed loop transfer function is just Cg over 1 plus Cg, and we are going to use our PI controller, which is given by this, and it can be reduced to this ratio. So we just have to use the feedback function, and it carries as argument the forward part and the feedback part. So the forward part here is just Cg. You can see we have Cg here, and the feedback part is just 1. We just have 1, we don't have any block. So going back to MATLAB, so let us now move to the feedback system. So line 59 defines my controller transfer function. For my gains, I define my Kp and Ki as 1s. And then for my controller transfer function, I use the TF function. It has 2 arguments. The coefficients of the numerator polynomial is the first argument, and the coefficients of the denominator polynomial is the second argument. So as you can see, I have Kp and Ki for the numerator, and for the denominator I have 1 and 0. So in order to find my closed loop transfer function, I use the feedback function, and the first argument is the forward part, which is Cg, and the second argument is the feedback part, which is 1, as we have seen in the diagram. So in order to visualize the performance of my closed loop transfer function to reference input, I just use the step function and I give it as argument the closed loop transfer function t. So running this section, so this is the step response of the closed loop transfer function. As you can see, a gain of 1 and 1 achieve this performance. And as you can see, this is the computation of my closed loop transfer function, which is a continuous time transfer function. So we can design different state feedback controllers using state space model. For our example, we are going to design a fault placement controller for our system. So, but the first thing to do in designing a state feedback controller is finding the controllability matrix. So, and we do that using the CTRB function, and the argument it takes are just the A and B matrix. So if we find the controllability matrix CB, we then find the rank. If the rank is equal to the order of the system, then the system is controllable. Otherwise, it is not controllable. So we know that we are dealing with a second order system. So we expect our rank to be equal to 2 before we can go ahead with our design. So the idea behind fault placement controller is that you place the faults of your closed loop system at a desired location. So my desired location are -2 and -5 for this example. So what I need to do is to find the gain or the gain matrix that will be able to achieve this requirement. And you do that using the place function, and it takes as argument A matrix, B matrix, and the location I want to place my closed loop faults. So this is just a brief discussion of fault placement. If you want a comprehensive discussion, I will attach a video at the end of this video for you to have an in-depth discussion. So clicking on this section, so as you can see, my rank is 2, which means my system is controllable, and the gain matrix that will be able to place my closed loop pulse at -2 and -5 are just 0.8 and 0.2. So finally, our discussion will end with the control system designer, which combines all the attributes that we have discussed earlier on and has even more features. So in order to go into the control system designer tool, you use the line 79. So you use the control system designer function and you give it as argument your plan as well as your controller. Alternatively, you can go to apps, then go to various apps. Here under control system design and analysis, I have my control systems designer, but it is simpler to use this line of code. So clicking on run section, so this opens up my control system designer. So by default, you see I have my Bode plot. This is the magnitude and this is the phase diagram. I have my root locus, I have my step response of the system. So you can add various plots within the control system designer. So if I click on new plot here, for example, I want to see the impulse response. So this is the impulse response. I just click on plot. So I have my impulse response here. So you can add different plots, and for each plot, I can save it by going to save as, and then I will save it within MATLAB. So one thing with control system designer is that by default, I have defined my controller, which is just s plus 1 over s, which means I have a gain of kp is 1 and ki is 1. So I can tune the performance of my controller using these plots, using the Bode plot, using the root locus plot, or even from the step response. So as you can see, I have a cycle, a red cycle here. If I drag out the cycle, so if you take a look, my gains are changing and the performance is also changing. So I can be moving the cycle in order to adjust the performance. As you can see, my phase margin is also changing and my gain margin is changing. So if I have like a satisfied response, I can import my response. So I can also use the root locus here. So I have the force as distress angles, so I can just move them in order to adjust the performance of my system. So moving them, you can see the performance is changing from the step response from the Bode plot. So I can be moving them until I achieve a desired performance. So you can see I'm changing the performance. So if you get a satisfied response, so these are the gains. The gains are here. So if I just go back to control system, and then I will just go to export, and then I will export my tune blocks. So my KP and KI are no longer one for this performance. So I just have to click on what I want to export. I want to export my controller C. I will then click on export, and then it will tell me the following variables already exist. Yes, it existed because I've already defined my KP and KI as 1. But I want a different KP and KI that would achieve this performance. So I will just say export anyway. So coming back to MATLAB and typing C, you see I have a different controller transfer function, and I have my KP as 1.9847 and my KI will just be 1.9847 times 3.33. So the control system designer has a lot of attributes that you can further explore. So if you want a comprehensive tutorial on using Simulink for control system, watch the video on the right. And as promised, if you want to learn more about pole placement control design, watch the video on the left. Please like and subscribe to the channel. Thank you for watching.